let's run through some of the other basic transformations a little quicker. Not going to do like a tabular workup. Let's just see what experimenting with Desmos tells us. That really gets you pretty results pretty quickly, although we always want to understand what's going on behind it. So I'm going to use this funky function g, which has these kind of straight line bits, kind of a paraboly bit, and kind of curvy bits. And I want to do some pretty normal things, just some pretty reasonable things to the algebra. So one of the things I can do is I can take that function g of x, and I'm going to do an outside transformation. There's going to be a transformation that's going to affect the vertical output variable, because I'm going to take g of x, whatever that number is, and then at the very end, that last thing I'll do on the outside the function, the parentheses, I'll put a minus. Let's activate that. Look at that for a sec. See if you can describe how those are related. In particular, what have I done to the black curve? That's the original g of x. I don't know why it's showing. Oh, that's right. Let's have it show up as black. There we go. The red curve, sorry. What have I done to the red curve to produce the blue curve? What I've done is I flipped it upside down. Right. So this guy didn't move. This flipped to here. This flipped to here. This stuff flipped up to here. So I've flipped it upside down. And so that minus sign on the outside flips it upside down. Let's see if that makes sense. So for example, 2 in the original graph, x equals 2 went to y equals, I think that's 4. Again, it's not showing me the vertical axis for some reason, but it's this height, that right there. And then when I put the minus sign on the outside, the same input, it was going to give me the 4, and then at the very end, I just flip it. Oh, it gives me a minus 4. So I don't change the horizontal. I'm using the same x value, but I'm flipping what I get, which is the vertical coordinate, and so it flips upside down. So I would call this a vertical flip, although sometimes when we talk about a flip or reflection, we often talk about the axis it reflects around, and this is reflecting around the x-axis. So that can be a little confusing. A vertical flip moves every point vertically, so what it's reflecting around is the stuff that doesn't move, which is the horizontal axis. So that's cool to know. We're going to record that in a second. What if we put the minus sign on the inside, though? Okay, well, remember what was the contrast between vertical and horizontal shifts? When we did something on the outside, it was a vertical transformation. It's changing the y values, but not the x values. This is going to change the x values, but not the y values. Okay, so notice that part of it actually seems to be staying in the same place, but this stuff on the left got flipped over to here, and this peaky thing got flipped over to here. So the green, and then this stuff is also symmetrical. So I made this so that it would have some asymmetrical bits and some symmetrical bits. Okay, so that's kind of interesting. And we'll talk about the issue of symmetry. It's absolutely related to this flip in class, but I think I'll save that for class. So what we're seeing is that if you took this and you flipped it around the y-axis, this stuff's going to go over here, this stuff's going to go over here, and it exactly makes that new green curve. Not shocking, because transformations that apply to the inner variable, that input variable, x, are going to be things that move in the horizontal direction. And so it's a reflection across the vertical axis, because that's what moves things horizontally. So let's summarize that over on this page. So a vertical flip is we're going to do y equals minus g of x, and a horizontal flip is going to be where we would do y equals g of minus x. And so that's is still with this theme of outer transformations, things that are done after you've done all the evaluation of the function, do move things vertically, and stuff that where you mess with the x variable, the input, that's going to be a horizontal transformation. So now I'm going to show you stretching and squeezing vertically or horizontally. That's not too hard to do. Let's go ahead and again, we'll go back to our original g. Remember, that's what that looked like. And now I'm just going to do y equals 2g of x. You might want to guess what this is going to look like, because I'm going to take all the same y values, and this is going to just double every single y value. Remember, that makes positive numbers more positive, negative numbers more negative, and 0, it doesn't change. So let's see what happens. All right, what this does is it stretches in the y variable. So this stuff is stretched up This guy's stretched up. It's exactly twice as far from the x-axis. This stuff's a little bit harder to see. These values were getting more and more negative. Now they're getting negative faster. They're stretched away from the axis. So this point stretched up. These guys stretched further away in y than they were before. I can make that more exaggerated by making it a 5 or a 10. I can make it pretty subtle, making it like a 1.2. So if I multiply by a number bigger than 1 on the outside, that will be a vertical stretch. Now what happens if I multiply by a number smaller than 1? Oh, it's a vertical squish. It's still the same shape. I haven't moved it left or right. Notice the zeros are always in the same place. I guess I didn't notice that before, but look. Those zeros, if the g of x is 0, if the y that I was going to get in the original function is 0, I'm not changing that. You multiply 0 by anything, you get 0. So back to the squish, 0.5, 0.25, it's a quarter as far from the axis. I'm really suppressing those values, 0.1. So all those values are getting closer. So any particular y value is getting squished. So that's the result of squishing it vertically. So we can summarize that. If you take y equals like a, well, let's do like 2g of x, or y equals 5g of x. This is like a times g of x with a greater than 1. Okay, and a squeeze, that's going to be y equals ag of x with a positive number, so I don't get a flip, but less than 1. If we combine those real quick, if I did like minus 0.1, that's squeezing and vertical flipping. Not shocking, because it's got the 0.1 in it, it's got the minus sign, it's just doing both actions, squeezing vertically and flipping vertically. Last thing, horizontal squeezing or stretching. You can totally guess what I'm going to do here, but again, it's a little backwards from what most people's intuition is. If I do g of 2x, think a second what you think that's going to do. You might, because I kind of prepped for it, you might have guessed that. But most people's intuition is like, whoa, I still kind of expected that to get bigger in x. Okay. What's going on here is, for example, the original function, I had to put in x equals 2 to get this height. If I'm actually also doubling, I'm taking that x and I first double it before I go into g. Well, then if I have x equals 1, then before g ever sees it, I double it to 2. It's as if I was plotting this point. So x equals 1. I double that. It's as if I'm actually plotting the red curve over 2, which indeed gives you this height. That's why the height closer to x equals 0, the height at x equals 1, is already up to what the old curve had to go out to x equals 2 for. Similarly, to get to the 0, the original function had to almost go all the way out to 4, but here, if I look at x equals 1.7, I double that first, then that gives me the x that the g thinks should be a 0. So again, we're kind of anticipating and undoing the doubling. We're actually putting x's that are 1/2 as big as they would need to be for the red curve. Because I'm doing the doubling, that makes them big enough to do what I want them to do. If I have like a 5, it's going to be squished even more. If I have a 10, it's squished even more. And you can probably guess, if I put in a number smaller than 1, that's how I make it bigger. I can totally do that. I just have to put in a coefficient here that's smaller than 1, not bigger than 1. So let's summarize it, and we'll be done. So stretch horizontally, that's y equals like g of 0.5x, or y equals g of like 0.1x. In other words, y equals g of ax with a small value, strangely enough. I'm not saying it's incomprehensible. It just tends to be against people's intuition. People get that wrong over and over again, all through later classes. But here it's going to be g of 2x. To squeeze it, then that's going to be something like put in big numbers, in other words, y equals g of ax, that's what a greater than 1 does. Okay, so we're getting a lot of practice with this.